Hello, welcome to hypothesis testing lesson 2. This is called hypothesis testing with the binomial distribution by finding critical regions, but I've broken it down into multiple parts and I want to go through something before we get to that. The first thing I want to go through is the concept of hypothesis testing, so we've got a really clear understanding of what's going on here, and I want to do it with a couple of examples. I'm going to claim that I've got a miracle packet of biscuits. This packet of biscuits that I've created can cure the common cold in just 3 days. Wow, that's pretty good. And we like biscuits, so I'd be happy with that. The hypotheses are, it's a packet of biscuits. It's not going to work. That is not going to cure the common cold in 3 days. There's nothing special about it. Those biscuits don't do anything. They're just regular biscuits. Or the alternate hypothesis is, wow, they really do work. Now, hold on. We're saying a couple of things there. And what we're saying there, we're saying two things. Not only are we saying that the biscuits are pretty special, that they do something, but we're also saying that the thing that they do is the good thing. Note that we're only interested in the one tail there. We're not interested in whether the thing that they do is bad. We're interested in, do they do something, and is that thing that they do good? Okay. Now, you're right. It does sound a bit far-fetched. Miracle packet of biscuits, I'm very skeptical. So the thing that we need to do is to do a test, the clinical trial. For this test, I've gone out and I've tested this packet of biscuits on 100 people, okay? And we're going to make conclusions for the whole population based on the results of this sample of 100 people. And that's one of the key things about hypothesis testing, is that what we do is we can't test on everyone. So we go out and we test on a sample and we look at whether the results of that sample are really significant. Can we be sure, or can we be confident enough that the results of that sample indicate that something really does work or not? The significance level I'm going to use for this is 5%. What we're saying there is, from our 100 people, 100%, from our 100 people, if 95% of them are cured within 3 days, then we'll accept that probably the packet of biscuits, on the balance of all the evidence, does work. Okay? What we're doing there is we're limiting ourselves to a 5% chance of incorrectly concluding that it works. So that's of making a false positive conclusion. I did go out and I tested my biscuits on 100 people, and 60 of them that ate the biscuits did recover within 3 days. I was pretty impressed. This figure does seem a little high, and you'd be right. I Googled it. To recover within 3 days of a cold, the average time that people recover from a cold is 7 to 10 days. Okay, so this is a little bit high, but is it high enough to conclude that the biscuits really work? Well, we set the limit at 95%, 95 people or more, before we'd be convinced of their effectiveness, and this falls short of that. So although it's a good result for our biscuits, it's not good enough for our hypothesis test. Our sample looks good on the whole, but maybe we're just lucky this time around with this particular sample. If we were to go out again, maybe only 20% would recover. Maybe it would be more, maybe it would be less. But the important thing is that it doesn't reach our 95% that we said would be our cut-off point. So there's our hobnobs. The conclusion. Now, it's really important that you do conclusion in context. Don't just say it works, it doesn't work, or don't just say I'm going to accept H1. What the exam is looking for, and the wording here is really important, is that you say something like, there is insufficient evidence to accept H1, and then you put it in context. We reject H1 and accept H0, that the new biscuits do not cure the common cold in just 3 days. Now, I said about the wording, okay? We're not saying that the biscuits definitely don't work, but what we're saying is that the results from our survey indicate that they don't. So on the balance of all the evidence that we've got before us, this is going to be the conclusion we're going to make. Now, this table will really help you out with the hypothesis testing exam questions. These are the things that you get marked on, and these are the things where you can score your marks. So, as I've said there, if you don't write anything else down today, copy this one down. And if you aim to fill in all these bits of information on your hypothesis testing exam questions, it's going to get you most of the way there. Okay? Define the variable. What are we talking about? P equals the probability of the biscuits being good. Write down your null and alternate hypotheses. H0, the null hypothesis, is the general case, the case that nothing's special, nothing's changed, everything's normal. We'll go with what we expect or are told the figures should be. H1 is the alternate one, the one that we're trying to test for. The significance level is usually given in the question. The one or two-tailed, that's within the wording of the question. If they don't indicate a greater than or a less than, then you're going to go two-tailed. But if they're looking for just one side, is the probability more or is the probability less, then you're going to go one-tailed. What's the probability of this occurring randomly? That's the bit where you have to then do your binomial distribution stuff and work that one out. And then you're going to compare that with the significance level. If the probability of that thing occurring randomly is lower than the significance level, then you're going to conclude that, wow, under H0, that thing had such a low chance of happening that it was so unlikely that perhaps, just perhaps, H1 must be true. And that's where we decide whether we're going to accept or reject the null hypothesis. And we conclude in context. Going back to that accept or reject the null hypothesis, that is the easiest way to word your answer and to save you getting confused when you're writing these things down. Okay, I said I'd do two examples, so here comes the second example. The biscuits thing, it was a bit silly, let's face it. So let's have scenario 2, developing a vaccine. We want to test whether a new vaccine can cure a virus. So this is a bit more realistic now. This is, real life stuff. The hypotheses are going to be the vaccine is ineffective, or the converse of any of the things I'm about to list down under H1. Because for the vaccine to be used and to be usable, all of these things have got to apply. It's got to work, it's got to be safe, no serious side effects, it can be manufactured quickly in measured doses, and so on and so on and so on. So ultimately, we're going to be giving this to a great many people. We've got to be really sure of our conclusions here, okay? A 5% significance level, that's not going to cut it. We've got to be really sure. So what do? The clinical trial, we use a much larger sample, okay? And within that sample, we've got to check and test on all sorts of different variables as well. Ages, genders, so on and so on and so on, okay? The significance level, we don't want to be 5% or 95% sure. We're going to be much more sure than that. So we're going to use a much lower significance level, okay? The numbers I've put here, they are pretty much what I think would be appropriate. In reality, I think you're looking at something along those lines, but don't quote me on the exact figures here, okay? Now, the thing is that 0.1%, that might sound really, really small. However, if you're talking about testing this or using this on the whole world, 0.1% of 7 billion people is still 7 million. So we've got to get this right, okay? What have we got here? In order for the vaccine to be approved for general use, the trial must demonstrate sufficient evidence that there is less than a 0.1% chance that the sample would have recovered without the vaccine anyway. So i.e., we're saying that there's a less than 0.1% chance that our conclusion would be wrong. We don't want to have what's known as a false positive or a type 1 error. We falsely claim that the vaccine works when in fact it doesn't. There are two ways of doing hypothesis testing. A little recap for you. This is a question like what you did last lesson. Can you please stop the video, have a go at the question, and we'll talk through it in a second. In fact, don't stop just yet. Can you stop on this screen here, please? Can you aim to fill in all of the blank spaces in the table? Right, so let's have a look through and see how you did. Define the variable. The variable is the variable P, which is the probability of success. Your null and alternate hypotheses are H0, null hypothesis, is that P is in fact 0.6. H1, the alternate hypothesis, is that P is less than 0.6, lower than 0.6. So I can read into that it is one-tailed. The significance level is 5%, just reading from the question. As I said, one-tailed because it's lower than 0.6. What's the probability of this occurring randomly? So that's where I've chucked it in the calculator. 7c2 times by 0.6 to the power of 2 times by 0.4 fail to the power of 5. That gives me 0.077, which looks close to 5%, but it is in fact greater than 5%. So this 0.077 is greater than 5%, and so therefore, although this thing was unlikely, it was really quite unlikely, it was more likely than our significance level. And so because it was more likely, then you know what, it just could have happened. And so we're going to accept the null hypothesis. And that hypothesis is that there is insufficient evidence to accept H1. We accept that the probability remains as 0.6. There are two methods of hypothesis testing. The method one that you've used so far, and we just used here, is that we compare the probability of the given result or a more extreme one occurring, and then compare that to the significance level. So if it is likely to have occurred, more likely than the significance level, then we're gonna accept H0. If it's less likely than the significance level, then we're going to accept H1. The other way we could have done it, method 2, which we'll go on to today, is that we'll find out what values would have actually given us an alternate conclusion, and then we'll compare those with the given result, and we'll see if our given result is amongst those. If our given result is amongst those that form the critical region, then we'll accept H1. Otherwise, it's going to be H0. So here we go. There's a lot of information on this slide. I'll talk you through it. So we've got X follows a binomial distribution with 7 trials, and the probability of success is 0.6. So X follows binomial distribution 7, 0.6. This feels familiar. It's very similar to the question you just did. The illustration over there on the right shows probabilities of obtaining between 0 and 7 successes. You can see that the bars go up to, what's that, 29% in the middle there for a value of 4. They're definitely skewed towards the top end, but then they should be because we're more likely to have a success because the probability is 0.6. So we can then use this information, the bar chart, to answer questions such as, what values of X have a probability of less than or equal to 5%? So we would just look through the bar chart and see where does that 5% actually begin? And I can see in the yellow bit, 0.2 plus 1.7, that gives me 1.9. Well, that's less than 5%. But if I then include the next bar for where X equals 2, then adding those together, it makes 9.6. So somewhere in between there is where 5% is. So the answer to part A, what would be the values that give us less than or equal to 5%? Well, it's just the values of 0 and 1. And we note that they actually make 1%, 1.9%. If we want the values of X which give us less than or equal to 10%, then we're going to go up to, and we're going to include 2 as well, because those ones add up to 9.6%. If we go further than that, then if we include the value for X equals 3, we're bumping a whole another 19% in there, which is going to be way over our 10%. Okay, the values of X mentioned here in the yellow bit, if you're talking 5%, or the orange bit for 10%, they're said to form the critical region, the region in which we would be accepting H1. Okay. What's this last bit? If we are only considering cumulative less than values or cumulative greater than values, then this is said to be one-tailed. So if we're only talking about one end of this thing, we're talking one-tailed. If we want to consider both ends, then that's said to be two-tailed. And in that case, we have to find out what are the less than values at one end and what are the greater than values at the other end. So my turn. I'll do this question for you. You can see I've already done it, and I'll talk you through it. So here's the distribution. X follows binomial distribution where n is 12 and the probability of success is a half. So it's a bit like, imagine flipping a coin 12 times. And here's all the different solutions or values we can get. We can get, let's say, the heads coming up no times, 1 time, 5 times, 8 times, and so on. Okay, just one note there. I know you're going to say it. How come the values for 0 and 12 are in fact 0? It's just because of rounding. Okay, so they're really, really unlikely. There's some other decimals going on there, just not shown here. So, question A. What are the values of x which form the critical region of less than values which got a probability less than or equal to 5%? So I'm counting up, I'm looking in there, I'm looking to add them all up till I get 5%. So 0 has got a probability of 0, 1 has got a probability of 0.3, 2 has got a probability of 1.6, that adds up to 1.9, yeah, I can see that. If I add 3 in there, then I'm going to be going up to 7.3. So I don't want to add in 3. So my values are 0, 1, and 2. Question B, what about the less than values which have got less than or equal to 10%? Okay, so this time I'm going to include 0, 1, and 2, and I'm also going to include 3, but if I include 4, that would take me to 19.4%, so I'm not. I'm going to stop at 3, which takes me to 7.3%. That's the highest value I can go up to, so that my percentage, cumulative percentage, is still less than 10%. So it's 0, 1, 2, or 3 this time. Part C, what about the more than values, which are less than 5%? Well, I'm very lucky here, in fact, because this is a symmetrical distribution. So this time, less than or equal to 5% is going to be the values of 12, 11, 10. You can't see me, but I'm nodding along as I'm counting backwards from the end of the graph. 12, 11, 10. That's where I get those values there. If I want more than values with a probability of less than or equal to 10%, then I'm going to include that next one down as well. So it's 12, 11, 10, and 9. But I'm not going to include 8 because that would take me to 19.4. All right, that was my turn. Now your turn. So here's your question. Symmetrical distribution again, lucky you. N is 15 this time. Can you just do exactly as I just did for those 4 questions, please? And your answers are 0, 1, 2, and 3, 0, 1, 2, 3, and 4, 15, 14, 13, 12, and 15, 14, 13, 12, 11. Hopefully that went okay. And you can see I've indicated the probabilities up there for you on the diagram. Okay, what about doing it again, but without the graph? So this time you're going to jump on your calculators, you're going to put it into binomial cumulative distribution mode, and you're going to be trying out values of x which get you either side of 5%, 10%, and then you're going to be looking for the other end, either side of 95% and 90%, because we're counting back from 100. And your answers this time are all the values 0 to 51, all the values 0 to 53, 67 up to 100, and 69 up to 100. There you go. Okay, from this point onwards, what I want you to do is continue with the questions in this slideshow on your own. You can get to the slideshow from the delivery map as usual. Answers are included in the slides as you go along, so you can check yours. Now, as I said, and as you did in that last question, you're going to put your calculator into binomial CD mode, not PD, CD mode, to test and check values either side of the significance level. Okay, so you're looking for what values of x give you probabilities either side of. So if it's a two-tailed test, you're going to half that 5%. So either side of 2.5% and 97.5%, etc. I will leave you there. Have fun.